equipment and 3D scanning equipment. We also offer 3D printing and scanning services and a whole host of CAD software. What we're going to be doing today is demoing our line of 3D scanners from Artec, the Artec EVA and Artec Spider, and then we're also going to be demoing SpaceClaim, which is a parametric modeler. The gentleman on the other end of the screen here is Stuart Bell. He's my applications engineer, and he is going to be doing the demos first of the Artec scanners, and then we're going to take that data into SpaceClaim and show you guys SpaceClaim. If anyone has any questions as we move through, just type it into the search bar and we'll try and answer them as we move along. So Stu, why don't you start off with going through the cameras, I guess, on the scanners and kind of letting everyone know what they do and how the scanners work.
Absolutely. So hopefully everyone can hear me okay. As Matt said, we'll be working with the Artec scanners today. Over here we have the Artec EVA, and right next to it the Artec Spider. The Artec EVA is a two-camera system. The top camera here is its texture tracking camera. These are our structured light scanners, and instead of using specific sized tracking dots, they actually uses texture along with some pretty sophisticated geometry tracking algorithms. So this is a texture camera or a color camera, and the lower camera here is the geometry camera, and then the center piece here with a ring of white LEDs that you'll see flashing on the smaller scanner that I'm going to demo today. That is the actual projector, projects the grid of structured light. Over here on the Spider, this is actually a 4-camera system, so you have 3 geometry cameras and a texture camera. The EVA and the Spider are very similar in functionality in terms of how your user controls are laid out. They both have user controls on the back here. Let me adjust the webcam so you can see what I'm talking about a little better. User controls on the back, so you can be away from your screen or away from your keyboard to more functionally scan. Both of them user controls. Both are point and scan, line of sight scanning. The Spider scans in a blue wavelength. It's actually a blue structured light, where the EVA is a white structured light. Both have LED light sources on the front. As I said, the 4 cameras. This is actually our projector over here. So if you look very closely, you may be able to see the blue light emanating from there as I'm scanning. It usually gets overrun by the white LEDs, which are just a light source for the texture. And then, of course, our 3 cameras. They are both point and scan. So I'm going to just get to scanning here and kind of show how they work. I'll get a geometric part set up here first. Tweak my webcam again.
So Stu is scanning the smaller parts there with the Artec Spider. The Spider is designed for parts that are about 10 inches cubed down to about 1 centimeter cubed, so fairly smaller parts. The EVA is designed for larger parts, about 10 inches cubed up to about 10 feet cubed. So they can both be used in the same project environment. So if you wanted to scan a vehicle, you would do most of the scanning with the EVA, but if you wanted high detail on, say, the door handle, you would scan that with the Spider. They're pretty close in accuracy. The Spider accuracy is right around 0.02 of an inch, and the EVA is right around 0.04 of an inch. And they are fully mobile. You can take them out in the field, and they do capture full color, as we'll see here in a minute. So I think Stu's going to scan that little block with the Spider.
I am. That is true. Let me double check. I think I lost a connection for a second here. There we go. Just reseat that. So while I'm doing that, the scanners are USB cable connected and have a power supply separate, both strain relief, as you'll see on the back as I'm scanning. Here we go, initializing the scanner. Here we go. So as I'm scanning here, you'll see a couple different things coming up on my screen, which hopefully you are all seeing just fine. On the left side of my scanning screen, you'll see a green bar that has some numbers and some variation in the color. The green bar is actually sort of a distance meter, and it's letting me know where I'm acquiring data and how far from my central kind of focus point. That's more or less letting me know where I am in my scanning volume or my depth of field, if you want to think of things in terms of photography. To the right of that is actually a sort of a preview of what I'm scanning, and within that you'll see there's a green amorphic blob, and that is actually what the scanner is bringing in. So I'm going to do one scan. We're using a turntable today that allows us to scan all the way around an object pretty quickly. Turn that up real quick. Okay, and start another scan. As I said before, they are line of sight scanners, so they taking a couple different views of an object allows us to fully capture and accurately capture the geometry itself. The scanning process itself, the physical scanning process, is much, I always often equate it to spraying a car. It's a very smooth and often very quick process as I just move around the object and fill in all the details. And utilizing the EVA would be exactly the same as this. You can actually, as Matt said, use both in the same project environment. The EVA is just going to have a significantly larger field of view and not pick up as much of the fine details, but certainly much more of the overall size of the object very quickly. I've got a couple scans here. This should be all I need for an object this simple. So I'm just going to run through a quick, in the latest version in the Studio 11, which is what we're using now, which just came out early this summer. Artec introduced a method called autopilot to actually make scanning very, very quickly, and as a pro user of the software has made my job very, very easy. So we're going to run through a couple registration algorithms, and then it's actually going to walk me through the process to turning these two sets of raw data into an STL or a PLY OBJ, so on. So it's going to kind of, just as a wizard as you might use in Microsoft Word or something like that, it's just going to walk me straight through, giving me some prompts. It also gives me really great feedback in terms of I can come up here and click into here, and it's going to give me some visual representations of what a bad geometry or good geometry is. When scanning, since the scanner is primarily geometry-based, it wants to see things that are rich in geometry, a lot of variation, very little symmetry, or at least variation in the symmetry, lots of unique geometry. So big flat surfaces, especially with something with the spider where you're only looking at about a postage car worth of data or area at the same time, it can kind of confuse one section of a flat surface with another. So it's going to walk me through some of that, object size, give me some feedback here, so on. And then it's going to allow me to say I can put texture on this. Since we are taking full color pictures, I can make this a full color scan. So really wonderful if we're doing scanning in products for digital I'm thinking of shopping, scanning in full 3D models of consumer products and being able to put them up on a website and have them rotate them, view them, see things like that. I'm going to skip putting texture on this one because it's a boring gray block, and we don't want to watch a green bar go from left to right for any longer than we absolutely have to. So once I have that done, I can click on Next here. It's going to prompt me here. One of the things that we really feel Artec shines in is the data editing. Click here. When I captured this, I certainly captured a fair share of the turntable that it was sitting on. I don't want that in my data set. Using the editing tools here, I can quite quickly come in, and I'm just going to use one that takes a sample and is going to just allow me to get a cutting plane in here. I'm going to get my cutting plane. Easy as that. Clean up the data. Can come in and use my paintbrush to get a little bit more of that outlying data, a little bit of noise in the scan, just like that. Same thing with the other view. in many other scanning softwares, Matt and I have been doing this for about 3 years, and we've worked in many different scanning environments. This is by far away the fastest that we've worked in, and for that reason, it's one of our, certainly our favorites. So it's going to
this process with I'm sorry, Stu. This process with other scanners where Stu just spent 30 seconds cleaning this up, that could be an hour or 2 hours with other scanners we've represented in the past. So we're really happy, especially with the new updates from Studio 11 this year, with the auto alignment and all this stuff. It just kind of makes it simple for the user, a little bit more intuitive. You can also do this manually if you have a little bit tougher geometry. Sometimes the software struggles, but you can always do this manually, and it's basically just connecting 3 common points between the scans and letting the software kind of suck the scans together into your keystone scan. And you can kind of see there each scan is its own individual color, so you can kind of tell where you are in your project environment and what scan you're working with here.
Yeah, and I'll actually show the manual alignment on the next. I'll do one more demo scan before we move on to the software portion, but I'll show the manual alignment. The autopilot, as I said earlier, has just made this process so quick and so easy, especially for new users. We had one of our fellow employees here at 3D Printing Colorado was curious to learn scanning, and he sat down and using Studio 11 and the autopilot was able to, in an afternoon, learn how to scan very effectively and efficiently, and can go out and use the manual tools that are walked through an autopilot because they're just all there and you still have control over them instead of just a one-button wizard. So it's a nice melding of keeping the skills and the data in your control as well as doing a lot of the work for you. So what it's doing right now is we just ran through a serial registration and a global registration, just moving all the data that we scanned into one sort of single coordinate system, and it's working through theirs. Outlier removal just basically looks at all that data and runs an algorithm that says anything that's 2 standard deviations outside of the average, deletes it. Last and next step we're running through here is the fusion. That is the term Artec uses for taking what is effectively a point cloud, which is what we look at the raw data in it. We get to preview it using the graphics card, but it's actually just a whole bunch of little data points. The fusion is taking all those data points and drawing triangles between them. It's turning them into polygons. In this case, triangles. Turning it so we could export it as an STL or an OBJ. Or PLY. You can export just the raw data in its point cloud format. There are some applications where that is very useful. There are a few standardized, and I'll show that when we get to that point into the saving portion. But there's still a few point cloud formats you can export as. But if you're going to go to 3D printing or what we're going to do into the reverse engineering or the modification, you primarily want to be working with a polygon format. STL is what we'll export. Step number 5 there was a small object filter. It's much like the outlier removal, but this is for any solid geometry that happen to be hanging out, little globs of data that the machine sort of turned into solid. It's just going to remove that and leave us with our principal data set here. And mesh simplification is it's going to run and say, I have it set, and you can let's tweak these settings elsewhere. It's going to get it to the lowest possible polygon count we can without changing the fundamental shape or without going past a certain level of error, a certain level of accuracy. So this is our metal block. We can see if I click into here, we're at exactly 1 million polygons. You can see there's a little bit of rough texture here. This is actually a painted block, so it has a lot of variation in its texture.
Yeah, Stu, can you hold that up to the camera a little bit to show that all of those kind of inconsistencies in the surface are actually in the block there? That's not scan data, bad scan data. That's just exactly what the block looks like there.
And of course, our high def webcam here is not necessarily up to the task of showing it. I can come through and I can actually scrub out some of these inconsistencies. There's quite a nice set of tools here within mesh editing tools within the program. I'm just going to use a smoothing brush real quick. I can come in and just normalize some of this texture. I can also come and use an automatic. There's a smoothing application here. Smoothing can run the risk of eliminating some features we may want to preserve. There's also a nice defeature brush here, where I can actually go through and get rid of spots of data. This is a feature that I ran a cylinder down and out and through, and I'm just going to clean them up. Don't really need them in our next step. Give that just a second to run. While we're doing that, I'm going to queue up the next piece here. This is actually a 3D printed, I believe it's a hyena skull that we pulled off of, the data was originally from the Smithsonian,
I think. Yeah.
Yeah. So we're actually going to scan in, I don't like that, this piece here. And we've seen a lot of these scanners being used for scanning in museum collections, artifacts, and then taking and 3D printing them so you can have them as hands-on pieces without worrying about damaging the original specimen. So exactly like the block, just get to scanning here. Let the scanner click in.
So as you can see, the scanners really don't care what they're scanning. The previous part was kind of a mechanical type of part. This is more of an organic kind of shape. The scanners are line of sight. They just really don't care what types of parts they're scanning in here.
Software's being a little slow. Often when we're running as many applications as we are, especially with GoToWebinar, it just lags behind a little bit. All right, so I'm going to turn up my brightness a little bit just so we can see the model. You can adjust many different settings on the scanner. We won't get too much into that, but you can, things like digitally altering what would be your aperture, turning up the intensity of the LEDs to get around scanning things that are very dark in color, plastic injection molded parts, or very bright, machined aluminum, things like that. So you have control of your scanner at nearly every level. So we'll do a quick scan.
So typical parts that are a little bit tougher to scan are shiny black parts, things like that, and machined parts, like machined aluminum parts. We have several workarounds that we work with, but the one that works pretty much the best is Walgreens foot spray. Just some dusting it with some powder knocks down the shine, and you're able to scan the parts, and it just wipes off. So that's what we use. Other people use children's paint, things like that wash off pretty easily. But we found that the $2 can of Walgreens foot spray works pretty well for most applications if the part's a little bit too shiny for the scanner.
So this one's a nice sample part because it has lots of nice little inclusions and hollow point spots and things that are very difficult to get the scanner down in. So it's a good piece to get lots of different angles on and show. Of course, the interior here of where the spinal column would have connected and things like that, not going to get all the way inside, so that's going to end up being a set of missing data. I believe this scan was originally built with a CT scanner that the Smithsonian was using. But for show and tell purposes, this is a great data set. For the tracking, as I mentioned earlier, the scanners, Artec scanners are full color scanners. They use texture as a tracking. That's part of the reason why I have a raw wood grain turntable here, is the scanners really love the variation in the wood grain. And it allows me to scan hard objects, very symmetrical objects, and I just have to, it can use the texture of the turntable to as my tracking, so I don't have to alter an object or do anything. This one is certainly has plenty of geometric variation in it, so that's not so much a concern with this, but something more along the lines of this jawbone here can have some nice symmetry to it. Certainly not as much in the teeth, but some nice symmetry to it. So the wood grain helps with that. All right, so we went through the autopilot before. I'm just going to run through the manual process and show it's all the same steps, just a few more button clicks. And click out of scanning, it's going to run our fine registration process. Much of scanning is, as many of you probably know from the CAD world, is just watching green bars go from left to right. Sometimes they're not green. In Artec, they're green. So we're going to skip right down to editor here. Same tool I was using before. Quick cutoff plane. Actually, I'm going to skip back out, and I'm actually going to use the positioning tool. We scanned many different orientations, and if I turn on the grid, you can see that I am not aligned to X, Y, and Z. So I'm actually going to just quickly use the data that I want to delete, but it's nice and flat, so I can align this, at least get it sitting on the plane that I want it on, apply. And now I can go in and quickly eliminate that data. Once again, that level of data manipulation is much slower in other programs. And I don't have to do it with every scan because I'm going to use that first scan as my keystone when I go to my alignments.
While we're waiting for Stu to clean up some of this data, it might be a good time if anyone has any questions to write in. We can answer those while he's cleaning this stuff up for you.
Let's see.
Educational discounts on scanners. Yes, there is a 10% educational discount for the scanners. So everything that you would need, depending on which scanner or a bundle, is included in a turnkey price. So you do end up saving quite a bit of money, roughly about $7,500 if you buy both scanners at the same time in a bundle. Other things you're going to need is a license of Artec Studio 11. With the EDU discounts, you get free updates for 2 years. So any updates to Studio 11 you would get, but then also if you go into Studio 12 or 13 or the next updates on these scanners, you automatically get those for the next 2 years. You also get 20 free, with education you actually don't pay for the software. For EDU you get 20 free licenses of Studio 11 and then Studio 12 when that comes out. So other than that, other than the scanners, you might consider a battery pack, which allows you to be mobile. And then install and training is always a big one. We either do that via GoToMeeting, what we're doing now, or we actually Stuart travels on site, on campus, and that sort of a thing. All right. What other? Stu, there's a question of how can you distinguish between hollow and solid objects?
Sure, I can.
That one.
Yeah, I can show that. There's a couple different ways. In terms of distinguishing in the program, let me click over here. There we go. We can actually let me get this running, and then I'll answer your question. I can certainly see if there are holes in my objects as I'm scanning. I can see through what comes up as black on my screen here is actually the back side of my polygons. The front side is assigned a color. Back side is just represented as black. So I can see it there. I can also, if I close out here, and I'll actually hide these guys real quick. I can come in and I actually have the ability to believe it's up here. Can actually pick a plane and do a cutting plane. But Studio 11 is primarily built to show us the outside so we can get our scanning and get exported. So what that really brings us to is our next level, our CAD software. And today we're going to be looking primarily at SpaceClaim. So I've got a few of these prepped already. Here's our metal block I did a little earlier. And one I did early in the scan, and I actually went through and took and turned our skull here into a mesh a little earlier this morning, so we didn't have to wait for those green bars. So I've exported those, and I've brought those over into SpaceClaim. And here is actually our mesh. So SpaceClaim is a full-blown CAD. Yes?
Hey, Stu, before we jump into SpaceClaim, let's get these questions answered for the scanners.
Sure.
One here is the turntable instrumented in any way? It looks like the scanner can calculate how the target is rotating in real time. That is, there's no motor or anything in that turntable. It's just basically a lazy Susan. That's all you would really need. I think we bought it at Home Depot for $20. And the scanner, it does pick up that you're rotating the part. It'd be just like if you were scanning a person with the EVA, say, you'd be walking around, but with this, you're just holding the scanner still and turning the turntable to capture the data. So I hope that answers that question.
And the turntable doesn't need to be instrumented or calculated back, in part because, as I mentioned, the tracking, the visual tracking on the wood grain helps the scanner understand it. And obviously, if I started scanning this and just spun the turntable very quickly, it would struggle to keep up. But a lot of that is the scanner building that object is based on its ability to recognize the geometry and track the actual texture in the background.
Okay, next question is there a general rule of thumb for intricate part inclusion, such as how deep a hole can be scanned at various diameters? Yes, there are some limitations with holes and things like that. These scanners are line of sight. Stu, can you kind of talk a little bit about holes and things like that?
Yeah, absolutely. So there's not a single sort of out loud rule that I use when I go to do my scans, but this is the metal block here is a good example. These cylinders here in the cone and these cylinders here are, if I remember correctly, just a little more than 1/4 inch in depth. They are going to give me no problems whatsoever, certainly because I can view them on multiple sides. The more a hole is visible, especially if it's a hole that goes through or something like that, the better data you can get. And certainly we saw that when I was working with the raw data, and I can pull it up and show it here again. The holes that are actually through here and this pattern of holes here are not going to give me anything but suggestions. What I find when it comes to doing the reverse engineering is I can better get location of these holes than actual diameter and depth. I can get location of these holes and then combine that with a pair of calipers and depth locators and things like that, some more traditional reverse engineering tools. So it very much depends, and the spider is going to be much better at getting data in here, these data inside of these smaller holes than the EVA.
Okay, next question. Objects which are made out of heterogeneous materials, can you capture the detail made from heterogeneous materials? So I think that's multiple, correct me if I'm wrong, Stu, but multiple material items. Is that kind of what you're thinking on that one?
I believe you know, I'm not entirely sure, but we'll address both what I think it is. If it's a porous or a material that light is going to pass through, there are actually some 3D printed parts that are so porous in nature that they're actually very difficult to scan because the light passes through them. As far as multiple material types, things like that, the only thing the scanner really struggles through is anything that it cannot. It's not going to bounce light back at its sensors. Any sort of rubber, any sort of rubber-like materials going to be fine, but clear glass is certainly not going to scan in. We actually have a project that's sitting in queue for us in our services bureau that is a couple glass features, and we'll have to dust those and basically paint those in so they're visible. But everything else, if you're scanning, you know, from everything that's here, it's not going to have a problem whatsoever. Or even adding in injection molded plastics, it's the contrast and in the ability for light to pass through it that are really going to make scanning difficult. Just yesterday we scanned a fiberglass, steel, and bronze sculpture that had varying colors and everything like that, and everything. No issues whatsoever.
There are workarounds for most parts. There are tips and tricks that we can teach people. If you have individual questions, I'll be reaching out to you later on, and we can kind of go over those specific cases. So I think that's it for the scanning questions. So I think we're ready to move on to SpaceClaim. This is a program from ANSYS that we really like, and Stu's going to kind of dive in here and show it to you.
Yeah, and so I'll start off at the very beginning and do a quick just walkthrough of what SpaceClaim is and what makes SpaceClaim different. SpaceClaim has a long pedigree in the CAD world. One of the founders of, or one of the driving forces of the SolidWorks world, and one of the driving forces of the Pro-E, after leaving their respective companies, got together and wanted to start a CAD company that CAD software, create a CAD software that everyone could use, and the result was eventually SpaceClaim. And SpaceClaim is a what we call a direct modeler. So for those of you who are familiar with the CAD world, we'll notice a few things a little different about the software here. Over here, and you'll notice that even more as I go along. Over here we have our structure tree, options. Everything's going to look mostly the same, but it's just, as I said, a little different. So I'm going to start doing some sketches here, and not sure why it's doing that. Home. There we go. So sketching is going to be much the same. I'm going to be able to enter in dimensions. I can add features, everything like that. Where SpaceClaim sets itself apart is the next step. So I just sketched and got myself a basic square here. Instead of going to extrude or revolve, I'm actually going to use, they've condensed all that into one single tool called pull. I'm going to pick a surface here, which I turned my sketch into as soon as I clicked out of the sketching tool, and I can just begin actually working on my surface here. So SpaceClaim is not a parametric modeler when that it stores your feature tree over here, stores your sketch and assigns parent-child relationships and so on. It is a direct modeler, so I can very quickly and easily make iteration changes, especially if I click on the right thing. It's all based on pulling. The This gives you some advantages in being very quick to move from a napkin sketch to a 3D model, but also SpaceClaim is CAD neutral in that because it looks at features, everything from faces to lines out here, corners, to easily put fillets in or chamfers. It actually allows me to bring in an IGES file the same as I would a SpaceClaim file, a native SpaceClaim file, and even Inventor, Pro-E, SolidWorks, and CATIA, all just able to come in here. And I can eliminate things, I can move things, I can pull things. So it gives you it's really a tremendous tool for machinists, CAD managers who get lots of data from different sources and need to sometimes adjust things and are worried about collapsing feature trees and so on. One of the big reasons that we really love it in-house here is its ability to do reverse engineering or very quickly and cheaply. It's the cheapest option we have for reverse engineering. It also allows us to manipulate meshes like no other software that I know of. This is our metal block. I imported as an STL. Let me actually jump back, and I skipped over this part, and that's my apologies. I just wanted to show our exports. Here's what we are capable of exporting out of Studio 11. STLs, vermels, for those of you who don't know, are a color-mapped STL. We can actually apply our texture maps and export them for rendering in programs like Maya, 3D Studio Max, Photoshop, and so on. Also our OBJs, and then down here are very specific point cloud formats. So sorry for the digression there. So. This is our metal block, which I exported as a STL earlier. SpaceClaim actually has what they call the Facets tab, which are some tools that are primarily for prepping STLs for 3D printing, and primarily FDM 3D printing. Has some basic tools in terms of checking meshes and seeing, it's going to tell me if there are any holes, give me some feedback, how many vertices. No problems with this piece of geometry, which we would hope not. So I could ship this off to my 3D printer, no problem. I could also come in here and I could shell it. I could tell it I want it to be 1 millimeter. Run that real quick. The shelling program in SpaceClaim is quite tremendous, and we use it quite a bit in terms of prepping things for 3D printing. A lot of 3D printers, you want to save as much material as you possibly can. Of course, it's not going to like it to do it for me here. Yeah. So one of the questions that came up earlier was how do I know a body is hollow or something like that? I can actually work with the STL here just like I would a normal solvent. I just struck a cutting plane through here, so I'm actually looking at a cross section of my scan here, and this allows me to see as I'm going through my cross section, it's showing me the geometry of that area, so I can see it's doing its best to represent things as lines and mostly splines in here, but it also allows me to come in here and I can see little bits of inclusion here where a bit of bad geometry got mapped in. This then allows me to grab my paintbrush here. Oh, nope, excuse me. Take a sample of this here, and I can actually put a plane on that. So I just took a sample of the actual mesh data there and put a plane on the average of it. I'm going to move that plane up through the center of my block here. And going back to my cross-section tool, pick that, go to a normal 2, and come back in, and it's just like I would if I were sketching from scratch. I can start turning this into a solid. And you'll see it is giving me constrained feedback. I want that to be 90. And I can fit this out here. Corner tool. There we
And
go.
again, if anyone has any questions as we're moving through this, please feel free to ask questions.
So I've got my basic shape there. Going back to using my pull tools, my pull tool, I can then begin to fit my block. SpaceClaim is a little different in that I want to build something out and then just eliminate what I don't need. And from here, it's repeating the same process as many times as I need to establish my geometry. I can either come in and I can create this line using sketching and cut this off to get this piece here, or I can actually just grab this and pull the geometry to where I need it, and we can certainly get a best fit there. Pull, I can, excuse me, pull. I'm using an what we call the up to command, where I can pretty easily make all my features match one feature that I've already mapped. And it is not letting me select that. So we've started to work on our block. This is all well and good. This is going to be very similar to a lot of other reverse engineering programs. Sketching, constraining your sketches, and then making it match. Where SpaceClaim sort of differs is actually being able to take sketched and solids and change and alter meshes with them. If we were bringing this into the 3D printing world, and we actually just wanted our model to be a little different, I'm going to eliminate this feature. I actually wanted to thicken this out by, let's say, 10 millimeters. Oops, excuse me. And let's say make it a little wider here. And we'll just do a quick sketch here and add a feature. Maybe it. I've thickened my base. I've added a piece that I'm actually going to turn into a key channel on the bottom here. And separate those into two pieces. Turn on my mesh there. So I can come in here and just merge my two pieces here, and that should allow me to add that solid to that base there.
And Stu, we got a question here.
Absolutely.
Why do you need to reverse engineer and create a sketch? Can't we just use the scanning geometry for our analysis?
You can. It very much depends on what you're trying to accomplish. If you are looking to make iteration changes to legacy document to a legacy part, or even if you're looking to make a set of documents, CAD drawings for parts that don't have them, you will need to make it so you can call out dimensions, or maybe you need to change dimensions and so on. That's where the reverse engineering, or what the industry really prefers, we say, is is documentation comes in. You know, you can use STL data if you're going into things like finite element analysis, or even if you're just scanning a part and you want to compare as manufactured to your CAD. You can do that with just the scan data. This is more to take you to those next steps.
Yeah, we use a different program called Geomagic Control for the scan to CAD comparison. We're not demoing that today, but we will probably be doing a webinar in the near future on that program. There's also another question here. Is there a way to turn an organic mesh into a solid versus sketching on the scan data to create a solid, such as with the scanned hyena?
Yeah.
I'll let Stu get into this, but yes, there are other programs that we represent that we are not demoing today. So Stu, why don't you talk quickly about those other programs here?
Absolutely. There are other programs. We have two that actually we work with primarily. One that is called DesignX. It is a parametric-based modeler that is produced by Geomagic, which is a subsidiary of 3D Systems. It looks exactly like you're probably familiar if you're from the parametric world. You sketch like you do in SolidWorks, extrude like you do in SolidWorks, and everything like that. And it allows you to bring in the STL data, much like I did here, and begin working on it, but in more of a parametric fashion. There's another program that is very similar, parametric modeler, called DesignWorks, and it is actually a plugin for SolidWorks, Inventor, and so on, that isn't a standalone program like SpaceClaim or DesignX, but sits as a tool on your toolbar that allows you to import STL data and build your data in native SolidWorks format. And we can and will do a webinar coming up here in I think next month. We'll have a DesignWorks webinar. And then we also do, if you would like to see a one-on-one demo, we can do those. So all I wanted to finish, and I will get to the organic here absolutely next. All I wanted to show you is here, I just merged these here. I've cut these channels through, and if I were continuing to work, I'd go through and recut my clearance holes and everything, but this is now a 3D printable part. I can send this to the 3D printer, and as an STL I can also send it to, there are now several CAD CAM programs that will derive their tool paths and everything they need from STLs. Or if you're some of the older ones, you still need to take it to a step or an IGES, which you can keep continuing through the sketch and extrude and everything like that. So clicking over here to our skull, the question was about organics. Organics present a little bit more of a challenge. There is actually an option here to convert to solid. It'll do its best to basically wrap a NURB surface around the piece here and turn it into a solid. With something that is this organic, that can really be a problem, and we certainly don't want to sit and run. So instead, sit and watch a wheel spin around. I'm going to move to a new tool that SpaceClaim introduced in 2016, which is the Skin Surface tool. And this allows me to do much of what I described the Convert Solid tool does, but actually gives me some control over what I want to convert. And I'm actually just drawing a grid on the surface here. It's going to give me a node network, and I can change the node network up and down, but it's going to allow me to create surfaces on the mesh directly. Get the patch created here. And hide my facets. There's my node, or my node network, excuse me, is now a surface. You can see if we get in close, it's actually picked up a lot of the variation in the texture on the skull itself. What I would do if I were going to start recreating this and turning this into a step file would be to go through and clean all this up. Now, it can be a lot of work if you're trying to create this as a turn this whole thing into a patch network, a surface network. What we primarily use SpaceClaim for, and this tool in SpaceClaim, is to prepare basically jigs and fixturing for either 3D printing or sort of next steps of manufacturing. You saw me, you know, create some geometry and bring it up. You can do the same thing with the surfaces. If we wanted to give this some supports, we could build in supports for 3D printing, or I can actually use my surface here as a cutting tool. Let me show that real quick. Yeah, let's keep this one here. Let's skip over to the jawbone here because this is a really great one. I can come in and using my organic shapes here. Oops, not that one. How about that one? Any other questions while I'm showing off some of the functionality here?
The question was asked back before about educational pricing. There is also educational discounts for SpaceClaim. I don't have the pricing in front of me, but I know that they are pretty significant discounts. SpaceClaim just generally is about a third to a half of the price of SolidWorks, if people are familiar with that. So fairly inexpensive to begin with. With the EDU discounts, I know you get either 10 or 20 licenses for the price of one, something like that, or even bigger discounts than that. And if anyone has any specific questions about pricing, feel free to just email me, or I will be following up with you guys here in the next couple of days. Stu, why don't you explain to everyone what the process you're going through right
Sure.
now, what you're trying to.
Yeah, absolutely. So all I did was just I went and built a couple of surfaces on the front of the jawline here, and then created a sketch plane just a little further out from that. Just sketched a little bit with a spline, and then brought it up through my my surface files, and then cut that. Used those surfaces to cut the solid that I created, which allows me, you know, this could be a fixture if I was, you know, as I pull that out, it's going to continue out though, so you can kind of see here. Let me turn off this guy and this guy. You can kind of see it's actually made that imprint in my solid geometry, including this little bubble here as it transferred that over from the jawline there. So
What we use this, excuse me, Stu. What we use this tool quite a bit. One of the hot new things in 3D printing is printing out injection mold tooling. So you can take scan data, say for this jawbone, and if you wanted to do an injection molded part, you could do the negative, put a box around it, and then slice it in half, and then take out the jawbone, and you've got your top and bottom side for injection mold tooling. We've been using a printer called the ProJet 3600, and specifically a material called M3X, where you can create your own tooling. And that's kind of one of the hot new things in 3D printing this year. So we use SpaceClaim to create the molds for that 3D printing.
I can kind of show that. We'll do just a quick, take a quick impression of the teeth real quick here. Make sure we got all of them. Oops. There we go. So all I'm going to do is convert my rough box here, and it doesn't have to stay a box. I can come in and kind of optimize my shape. Match the geometry there. Maybe bring this guy in to there. And of course, it's often quite difficult to see what you're doing. So if I wanted, I can go back to my cross-section tool. And I can actually work on my solid geometry in the cross-section tool, which is one of my favorite features of SpaceClaim here. So once I've got that, I can go back to here. And I can just convert this guy to an STL, because we're going to print it. I can subtract the two shapes. And that'll take just a few seconds. Any other questions? Well, oh, look at that. She went a little quicker. So, and there's that. There's our shape. Clear up the screen with our teeth. I can now take that and I can export this as an STL, 3D print it. I can cast impressions off of this, or we can then begin to build a mold around this, or something to take it all the way through to, as Matt said, an injection mold, or whatever steps we want to go to next. And that's really what SpaceClaim is those next steps between your scan data and then making your scan data work for you. Any other questions? Anything anyone would like to see or hear about? SpaceClaim, just as people are writing out their questions, or we're thinking about their questions, SpaceClaim is a fully functional CAD program. The Facets tab is certainly the 3D Prep and the STL manipulation tab. There are also KeyShot and Dynamics. You'll see up here, KeyShot is a rendering program, a third-party rendering program that's built into SpaceClaim. Dynamics is a physics and analysis program. We can also sheet metal, ability to load in K tables, customize everything, build sheet metal. There are also repair and prepare tools for importing broken IGES and step files and preparing things for the machinist world, as well as just a good old-fashioned CAD program. Loft, sweep, revolve, everything you can do in every other program you can do in SpaceClaim as well. Without digging in too deep, there is a lot in here. So if someone would like to see SpaceClaim attempt to do something, we're more than happy to set up a one-on-one demo. And Matt, do you see any other questions out there?
Yeah. Let's see here.
Sorry, my question tab disappeared for a moment.
Will this scan process work for Inventor?
Yeah, absolutely. There is so the scanning software is a standalone software. It's just Studio 11, and then there is we talked about DesignWorks, and we used SolidWorks, but DesignWorks also has a plugin for Inventor. and allows you to send your STL data over to Inventor and work in your native CAD format. As far as bringing in STLs into Inventor, often your more traditional programs, SolidWorks, Inventor, struggle to pull geometry off of STLs. They try to see them as surface files. That's why DesignWorks exists, is to give you that tool.
Right, and I'll be following up with everyone that attended this webinar, and we can do specific demos of Geomagic Control or DesignWorks or any of the other programs that we represent. I would encourage you to go to our website, www.3dprintingcolorado, and you can kind of look over all of the printers, all of the scanners, all the software that we sell and service. And if you have specific questions about any of those, we will be able to address them individually. Other than that, it looks like most of the questions have been answered here. So we'd like to thank everyone for their time. We appreciate you joining us here today, and if there's anything else, we'll be following up here in the next couple of days. Thank you very much.
Thank you, everybody.
Have a good afternoon. Bye-bye.